Hello, welcome back everybody. Hope you enjoyed the first exercise and getting to use the new class chip. And in this second lecture, we're going to talk about metal oxide semiconductor transistors in sub-threshold operation. That means weak inversion, where the current will flow by diffusion from the source to the drain of the transistors as a kind of a gas of electrons flowing right along the surface interface. But we have quite a bit of stuff to do. So first I want to do the poll for lecture 1 and lab exercise sessions, give you an update on that. And then I want to go back to an interesting revisit to the cost of digital computation that I mentioned in the first lecture with a real example of a recurrent neural network hardware accelerator to show you just how incredibly efficient biology is compared to electronics now. And then we'll go through a little quiz for lecture 1. And I'll tell you a little bit about our standards for lab exercise reports, just to try to set a good tone in the beginning. And then we'll give you a preview of this week's lab exercise, which is measuring subthreshold field effect transistor current voltage characteristics. And then I'll start the main body of the lecture, which is about a little bit about the history of the MOSFET. A review again of the semiconductors. What is a MOSFET and what is CMOS? I mentioned that last time, but we'll do it again. And then the relation between physics of the transistors and the voltage sensitive nerve membrane. This is the kind of fundamental foundation of the original idea behind neuromorphic engineer, was rooted in this device physics analogy. And then we'll go through the MOS capacitor structure here, and talk about the different states that the surface can go into: accumulation, depletion, and inversion. And then we need to talk about capacitive dividers, which is there's a capacitor here and there's another depletion capacitor here, and they divide to control the surface potential. And that results in the so-called backgate and body effect parameter kappa, or 1 over n, as other communities know it, that determines how well the transistor current can be controlled by the gate voltage. And then finally, we'll go into the MOS transistor and subthreshold and weak inversion operation, and then you'll have the opportunity to see those and measure those results yourself in the exercise. So that's the program. But first, let's go through the feedback poll and a lab session update. Okay, now I want to give you a little preview of this week's lab exercise. This week you're actually going to use the Coach class chip, and on this class chip is an array of transistors like this. They're NFETs and PFETs. It's the same thing, either NFET or PFET, and they range over the following width over length, right? They're all 1 micron wide, but they range from very short, minimum length, 0.18 micron, all the way up to 2.88 microns. So very long, skinny transistors. So either short and rather wide, actually 1 micron is quite wide, to really long, skinny ones. And now using the digital multiplexer here, you can select one of these transistors and wire it up to Ninkau's current measurement, C2F circuit. It's current to frequency circuit. And I'll just explain how this circuit works so you know where these pulse counts are coming from that you measure using your Python code. So the current comes in here. Without telling you how this all works, the current is actually mirrored over here. It's copied. Either the P or N type current is selected, then it's mirrored again, it's copied again, either with 1-to-1 or 10-to-1 ratio. You can select which by this switch here, so you can decide to amplify the current before you go and measure the frequency. And then the current is mirrored again here, so it's copied again here. This is the current from the transistor, just a copy of it, or 10 times it. And then it goes into this current to frequency circuit, which basically just integrates the current on this capacitor, which is arranged in a feedback loop. So, and the feedback capacitor can again be chosen by this switch to be either 1 or 10. And then this feedback loop charges up this circuit until it crosses the threshold, Vref low and high. So it keeps doing this like a neuron, right? It's like an integrated fire circuit. It keeps going around, going up and down like this. And then what results is a stream of pulses that go off chip, and these are connected to the counter unit on the Teensy microcontroller. That just counts the number of pulses over some fixed integration time. And so now you can work out that the delta time between these spikes, these pulses here, is related to the difference in reference voltages. If you make those bigger, of course, delta T is bigger. Also, the size of this capacitor, C, it's the integration capacitor right here. And some other ratios like beta and alpha that have to do with whether you choose 10 to 1 here and here. And then from this delta T, now you can work out that the current, because the bigger the current, the smaller the delta T between the pulses. And so basically that's what you're going to be doing when you measure these transistors, is to sweep the gate voltage here, holding the source voltage constant, and measure the pulse frequency, and from that you can infer what the drain current is. Okay? I hope that's clear. Okay, now when you're writing up your report, turning in your Python notebook, please try to avoid these common mistakes in your lab reports. First of all, not discussing your data sufficiently. Think about a publication. The readers want to understand your reasoning with you. They want to be able to reproduce your results. So attempt to do it like you are writing a methods section of a paper. Another big mistake is using axes plot fonts that are too small. If you were using MATLAB, you would set the font size big to make it user-friendly. And this is like the #1 mistake that all beginning students make. They all make the things basically unreadable for the readers, which is annoying, just a sign of laziness. And another common mistake is not using crosshair axes when 0, 0 is relevant as the origin. For example, if you have a differential circuit, what you want is axes that go like this and then surrounded on both sides so that 0 is in the middle. Don't put because 0 is a natural point. So then your differential circuit will show its results around the axis. It's more natural, right? Also, another common mistake is forgetting to mention what your plot shows. Forgetting units on your axes, not labeling your figures with a caption. For example, figure 1, transistor drain current versus gate voltage, experiment 1. Insufficiently labeling your data. It's good to annotate your plots to indicate the slope of the curve or the XY intercepts. Using identical markers for all plots. Your curves should be distinguishable even by colorblind people. Forgetting units on measurements. For example, here is one directly quoted. Our conductance is 1.000653 E minus 10. What are the units? Is the reader supposed to guess that these are Siemens? Giving your measurements too many digits of precision. See this error here. Do your instruments really give you 7 digits of precision? You should know a little bit about precision, right? Or how precision propagates through multiple measurements. And a tip is to use notebook cell editing mode, which you're going to use a Python notebook by default, where sections are separated to generate your measurements. That way you can quickly change and repeat your measurements in plotting. So try to keep these things in mind, please. So now I'm going to give you a Blackboard summary of subthreshold FET operation live, and it gives you an opportunity to ask questions. And it's a little bit of a preview of all the material that will be shown in slides later. Okay, so now you've seen this cross-section, short summary kind of review on the Blackboard. Here's a cross-section of a complementary pair of field effect transistors. You have, again, a P-FET on the left that's sitting in an N-well. The source and drain are P-type, and you have an N-FET sitting in a P substrate with N-type source drain. And the gate of the transistor is separated from the channel by gate oxide. In between the transistors, there's field oxide, and each transistor has a source and a drain, which are interchangeable. So this is called a P-FET, this is called an N-FET, this is called an N-well, and a P-well. That's the substrate that the transistors sit in. And here are top and side views of field effect transistors. So a top view, if you actually drew the layout of this transistor, would have an active region in green and a polysilicon gate in red. And if you look at the side view with a cross-section like this, crossing from source to drain from the side, as people usually look at it, it looks like this, right? Just like we saw. The source here, drain here, and gate, and then oxide. But if you look at the view cutting across the transistors, all you're going to see is nothing, except that poly goes over thin oxide where the channel is, and then it goes up where the thick field oxide is. So this is called T-ox, or transistor oxide, and this is called F-ox, or FOX, which stands for field oxide. Okay, so then there's a set of standard symbols for transistors. So what we do usually is to indicate a PFET by using a bubble to indicate hole carriers. But many people draw transistors like this, where they have an arrow on the source side and it points from P to N. Right? This is commonly done by more traditional mainstream CMOS design groups, because although it's harder to see which is a PFET or an NFET, this arrow then indicates which side of the transistor the designer believes will be the source of the side of the transistor during operation, or the design side of the source of the transistor. Okay, but those are the symbols. And there's terminology. So NFET terminology is like this. The transistor has a drain, gate, and source. The source is called a source because it's a source of electrons at lower voltage. Electrons are negative, so they flow from lower voltage to higher voltage, and so the drain of the transistor of electrons is at a higher voltage. And the gate is such that putting positive charge on the gate here attracts electrons into the channel and increases the current. Similarly, for a PFET, we have a source, but this time of holes, which are positive, and those are at higher voltage. Holes flow from high voltage to low voltage, and so the drain of holes here is at a lower voltage. It's whichever terminal is at a lower voltage. And now the gate consists of putting negative charge here, attracts holes from the source, and increases the current in the transistor. That's the simplest way to think about it. And the basic function, the basic way that such transistors work is that the built-in potentials in the PN junctions here create an energy barrier like we saw last time, and in subthreshold, controlling the barrier height controls the diffusion current between the source and the drain. And you saw the video last time that the carriers are flying around in the source and drain semiconductor due to thermal activation with a scale of energy. In fact, if this barrier height here is 0.75 volts and the thermal activation energy is a 40th of a volt, remember KT is a 40th of a volt, 25 millivolts, then this scale is much exaggerated here. It should really all be happening in a width roughly the size of this bar here. So the question here, is the scale realistic at room temperature? And the answer is no, definitely not. The real barrier height is about 700 millivolts, and the KT over Q, the E-folding voltage for concentration, is only 25 millivolts, so the real scale of such E-folding would only be this big. But this is the situation when the source and drain are at the same potential and the gate is at 0 volts. So there's a built-in barrier, as you saw last time. If you now increase the gate voltage, make it positive, say 0.3 volts, so you put some positive charge on the gate relative to the source and the drain, which are at the same potential. Now you have a situation where some of the electrons from the source and drain can go into the channel. There's no net current because there's no concentration difference. But now if you put the drain at a high voltage, say 1 volt, you decrease the potential for electrons, because remember, electrons like to go to high voltage, right? They're negative, so they go downhill to high voltage. And now you have a situation where at the source you have a high concentration, at the drain you have 0 concentration because the barrier is very high, and as a result you get a net current flowing through the channel. That's the basic mechanism of current in subthreshold. That's all there is to it. And everything else is just eye candy on top of that. So now, what's the relation between transistors and neurons? So here is the way you measure voltage-dependent nerve membrane currents. You take an axon out of a squid, and a squid is an animal, with the tentacles, and that it can move by shooting water out the back, and that's how it can escape and capture prey and so on with its great suckers. But it has this giant axon, which is about 1 millimeter around, and it was used for a long, long time to measure basic functions of neurons. And so you can take this axon, which is the output of the neuron, and put it in a solution, and then put an electrode inside and outside this axon and measure the voltage across it. So then you can control the voltage across the membrane and also measure the current across the membrane. And what you observe here is that the current, which is on the scale where inward is down and outward is up across the membrane, you see that the total current is this current here, and it consists of two components. And one of those components is the so-called sodium current. It's an inward current, positive current, which makes the inside of the neuron go more positive relative to the outside. It starts out actually very negative, but it's a pulse of current that makes it go more positive. And that's how the spike is initiated. It's a positive feedback mechanism, as worked out by Hodgkin and Huxley, the Nobel Prize winning work of Hodgkin and Huxley. And so now you can ask, what is the voltage dependence of this sodium current? It has a complex time dependence, but what's the voltage dependence? And what you observe is something really cool. So here is a comparison of transistor and membrane channel currents with a test pulse potential, which I just showed you on the previous slide. There was a little pulse. You put in a test pulse to a particular voltage from the rest potential, which is very negative, and now you measure the relative maximum conductance of the membrane. And you see that it changes in this way. It increases with voltage, but it increases as a straight line on a log scale. That means that the increase is exponential with the voltage, right? Linear on a log scale. And interestingly, very interestingly, the slope of this potential is 3.9 millivolts to change the current by a factor of E. So the current changes by a factor of 2.7 with only about 4 millivolts of voltage change. So it's a very steep exponential. In fact, this is much, 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 much steeper than anything that electronics can achieve. But it is an exponential like electronics. If you measure a transistor, gate, drain current versus gate voltage, you get this exponential too. And you guys will all understand all about that. But you see that the transistor takes about 40 millivolts on the gate to change the current by 1 E-fold. So it's about 1/10 as steep. And so now you can ask yourself, how is it that biology achieves this incredible gain or transconductance in its voltage dependence? And this is key to how biology can work with a power supply of only 100 millivolts. I won't explain why. We'll discuss that another time. But why is it that the fundamental device physics of biology is able to achieve 10 times the exponential transconductance of biology? But they're both exponentials. So that's key, right? So now you can think, what's the analogy? See, neuron channels and transistors both depend on exponential Boltzmann distributions of concentration versus energy. So in neurons, the membrane ionic conductance caused by these pores in this voltage-gated sodium ion channel is exponentially dependent on the voltage across the neuron membrane. These devices here, these channels, the population of open channels depends exponentially on the potential across the barrier. But in transistors, the current flow in transistors is exponentially dependent on the barrier height between the source and the channel. And the population of carriers depends exponentially on the barrier height. So here it's different, right? It's fundamentally different. Here it's the population of open channels that depends exponentially on the voltage. And here's the population of charged carriers that's exponential with the voltage. So they're both exponential. They both depend on Boltzmann. But one depends on a population of open channels, and the other one depends on a population of actually carriers, electrons or holes. But still, there's that Boltzmann exponential in both, which is kind of fundamental, thermal physics. And so that was a big motivation to look at neuromorphic engineering in the beginning. So now let's go back to the transistor again. And look at this N-type MOS field effect transistor. I'll just talk more about terminology again. So this transistor, an N-type transistor, is built in a P-type substrate. It has a bulk, which is called a backgate, called VB, which is P plus connected to P. It's the same type, so there's no junction here. It's just a good electrical connection to this P-type substrate. And the transistor source and drain N regions are surrounded by a depletion region. Just as you saw last time between P-N junction, there's always a depletion region. So this is N plus here. This is P minus, so these are neutral regions here. But around this, there's actually this Pn depletion region. We only show it kind of as one side here. And actually in the channel, there's also a depletion region. And the current in the transistor depends on the combination of all these voltages, the bulk, the source, the gate, and the drain. And in particular, it depends directly on psi S, which is so-called surface potential. you can't have access directly to the source potential, but that's the potential matters that controls the current. And you always operate this transistor where Vs is bigger than 0 volts, Vb is 0, right? That's defined to be ground. That's the lowest voltage. Then the source voltage must be higher than that so that the junction is reverse biased, so N is higher than P. And then Vg and Vd are generally bigger than Vs when you operate this MOSFET. When you draw it as a circuit, you just draw these voltages that are biasing the different nodes of the transistor. So all voltages are referenced to this bulk voltage, Vb, which is 0, by definition 0 volts. So now let's look at this regimes of operation for a field effect transistor, which is dependent on the gate source voltage. So there are 3 regions: cutoff, where the surfaces accumulate; subthreshold, which is weak inversion, where the current flows through diffusion; and above threshold, which is strong inversion, where the current flows through drift. We're going to talk about subthreshold weak inversion regime this week. So now let's look. What does the drain current through the transistor look like as a function of the gate to source voltage on this axis here? So this is gate to source voltage from 0 to 5 volts, and this is the drain to source current in amps from 1 picoamp, 10 to the minus 12 amps, up to 1 milliamp, which is 10 to the minus 3 amps. And you can see some very characteristic behavior, which looks a lot like the neuron that I just showed you, right? It's exponential over about 1, 2, 3, 4, 5, 6, 7, at least 7 decades of current as you increase the gate voltage from 0 volts, and then it flattens out. And if you measure this, you'll see this is actually square law behavior. But square law behavior on an exponential scale looks almost flat. It just doesn't increase that fast. So that's what you guys are going to measure. Your mission should be to measure a curve like this. Of course, you'll have less dynamic range because the current to frequency circuit that you use has much less dynamic range than the source measure units that we used in the past, the Keithley source measure units. But you'll be able to get some parts of this curve. Okay, so in subthreshold and FET, the current is so-called diffusion current. And now I'm going to work out the equations of subthreshold current kind of from scratch. So you have a source, gate, and drain voltage. And now we define Z as the dimension along the channel from source to drain. And we have the edge of the conduction band where you have the electrons here. Here is the concentration at the source end of the channel, and here is the kind of concentration at the drain end of the channel. And now we know we assume that the current is diffusion current, so the current in amps is just given by the diffusion equation. It's the electron charge times the diffusion constant in meters squared per second times the concentration gradient in number per meter cubed per meter. Okay? Here, N is the carrier density and number per meter cubed, and D is the diffusion constant. So if we can work out the concentration gradient and know what the diffusion constant is, then we can work out the current. But what is this concentration at the drain and source end of the channel? You can work it out from complicated band theory, but now I'm going to give you the story which leaves out the really complicated physics, which is not that useful. So again, you have a surface potential psi s, which is defined here at the surface, at the source end of the channel. So now you know, because of Boltzmann-Fermi, the Fermi-Dirac distribution, and the fact that this conduction band is far from the Fermi level, that the concentration of electrons in the source end of the channel is some pre-exponential constant n0 times e to the minus theta s over ut. What is theta s? It's the barrier from the source to the channel at the source end. That's the Fermi-Dirac distribution. Some constant, which is dependent on temperature, times e to the minus barrier height in volts divided by the thermal voltage. Makes sense, right? Just exactly the Fermi-Dirac distribution. And then the concentration at the drain end is the same thing, but now the barrier is the drain barrier. So now you have the source and drain concentration, so you can work out the gradient of concentration, right? But first we need to work out the source barrier. So the source barrier is actually some built-in barrier. That's the built-in potential between the N and P regions, which we worked out last time. It's proportional to the thermal voltage times the log of the product of donor and acceptor concentrations divided by the square of intrinsic concentration. But it's this built-in barrier minus Q. You need that to change from volts to potential. Minus Q times psi S minus Vs. If you look at this, it's just how much the barrier is reduced or increased by a source voltage. Okay, so psi S is the potential here. Vs is the potential at the source. And if that voltage is 0, it's exactly the built-in barrier. And the same for the drain end. So now you know that the concentration gradient is dN dz. It's just the source concentration minus the drain concentration divided by the channel length, which is the drawn transistor length, or the effective transistor length. And so now you can just plug that in here, and you get that I is minus Q times the width of the transistor, because the wider the transistor is, the bigger the current, times the diffusion constant for electrons, times the gradient of concentration, which works out to be I0 e to the psi s over ut, times e to the minus Vd over ut minus e to the minus Vs over ut. So this comes from putting in this psi s into here, where you have here the Vs and the Vd. You can see the definitions of the constants over here. So that's the basic transistor equation. Now, do you see the problem? The problem with actually using this equation? The problem is right here, right? You don't know this psi s. You're controlling Vg, not psi s. So now we have to figure out how psi s is related to Vg. So let's see how that works. But before I go on to that, I want to point out that this transistor current has two contributions: a forward component, which is the contribution from the source, and a reverse component that's contribution from the drain, and they don't interact with each other. It's just a linear combination of those two currents, imagining that the density is 0 at the other end of the channel. It's exactly symmetrical. Okay, so we have the equation for the subthreshold current, but we don't directly control the surface potential, which is right here. So the question is, how is the surface potential related to the gate voltage? So we need to understand the effect of gate on surface potential. So let's consider a cross-section through this end fit right here in the middle of the channel. So now here is this MOS capacitor structure, taking off the source and drain and just considering the polysilicon conductive or metal gate connected to a gate voltage, separated by gate oxide from this P-type substrate. It's P-type because there's many mobile holes down here and very few mobile electrons. And there's also negative fixed ions, right, from this P-doping. So like I say, the circled plus here is a mobile hole. So now let's consider what happens when we change this gate voltage. Well, first we need to talk about something called, in this MOS capacitor structure, called accumulation. What do you think that means? Accumulation is like getting more, accumulating stuff, like accumulating junk, accumulating money. In the same way, accumulation here refers to the fact what happens at the surface here when it becomes more P-type. So if we make the gate voltage negative and put negative electrons onto the gate, that attracts positive holes to the surface, and the substrate becomes even more P-type, even more unfriendly for electrons. And so this arrows here indicate how the field lines from these mobile holes terminate on these mobile electrons up here. Okay? So this is called accumulation. The surface is accumulated with majority carrier. It's made more P-type. And then you have a flat band situation where the gate voltage is around 0 volts relative to the substrate. And the majority carrier density is just constant here, and it's equal to the dopant density. And now you have a very important region for subthreshold, which is called depletion. You can imagine what that is. You're pushing away these holes here by making the gate voltage positive, but not too positive, less than the threshold voltage, putting some positive charge on the gate. That pushes away these mobile holes here and leaves behind only the negative fixed ions. Okay, these are the atoms that you've doped the substrate with, which are acceptors, so negative ions. In depletion, the majority carriers get pushed away, the fixed ions end the charge field lines, and the depletion region, space charge region, is formed. So it's just like the p-n junction space charge region, but in this case you formed it by just pushing away the majority carriers. And finally, when you make the gate voltage positive enough, you get into the situation where all of a sudden charge rushes in from the sources and drains. If you go bigger than the so-called magic threshold voltage, put enough positive charge on the gate, and then you'll now induce mobile electrons, not these fixed ions, but mobile electrons, either thermally or by shining light on the thing, or in most cases by getting them from the source of the transistor. An inversion, mobile electrons are induced at the surface. The surface is inverted. It actually becomes N-type instead of P-type, right? Because now it's electron type. And the threshold is when the threshold voltage is, by definition, is when the mobile charge density equals the doping density. At least that's one definition of threshold. There are other ones too. Okay, so those are the different inversion regions of the channel. So now let's talk more specifically about a depletion capacitor, because that's important to understand how the gate voltage controls the surface potential. So what is a depletion capacitor? So again, you have the gate here, which is a conductor. You have the gate oxide, which is silicon dioxide insulator. You have the surface over where all the action happens. You have the depletion region with the fixed negative ions. And now the definition of capacitance is that it's the change in charge caused by a certain voltage. A big capacitance means you've got a lot of charge for a small voltage, or you have to put a lot of charge to create a small voltage, or vice versa. Either way, so that's a big capacitance. So let's see what happens if you now put some charge on like I just did. Okay, so you need more charge, but you can't get it from these because you used up all these fixed ions, all they're terminated to. So when you add more charge, they're going to appear further away, right? That's why it's a depletion capacitor, as I talked about last time. So as you increase the voltage on this depletion capacitor, the incremental capacitance actually gets smaller. So if you plot the capacitance as a function of the gate voltage, it actually decreases like this until you get to threshold voltage, and then it suddenly goes up to be just equal to the oxide capacitance, because all the new charge appears a mobile charge right at the surface. Okay, so that's the oxide capacitance, Cox, per unit area. So now let's talk about the influence of the gate on the surface potential. So we have the gate voltage, we have our insulator capacitor, which is Cox, we have a possible inversion region, which we're not considering now, we have a depletion region, and the Psi-S is exactly the voltage right exactly at the surface between these two capacitors. And then we have a depletion capacitor called C-dep, and then we have the surface potential. So the definition of this thing called kappa, which you're going to hear a lot, is that it's the change in the rate of change of the surface potential with gate voltage. And I'm now going to show you that that's equal to Cox divided by the sum of Cox plus C-dep. This is the famous capacitor divider equation. So why is that the equation that we should use? Let's see how that works. Let's talk about a gate depletion capacitor divider. So let's consider a change in the gate voltage with a Cox, a C-dep, and a particular charge sitting on this surface at this point on this capacitor. And now let's compute what's delta Psi-S caused by delta Vg. How do we do that? Well, the basic assumption we make is that this charge here doesn't change. So whatever charge we put on this capacitor, it also has to appear on this capacitor because no charge can be created or destroyed here. So the question is, how does changing Vg change Psi-S? So we know that Cv equals Q. We know the charge Q on Psi-S is constant. We're going to change V and hold Q constant. So how do we do that? We put some charge here. The same minus charge appears here. Because you've put minus charge here, there must be plus charge left behind here, and that's balanced by minus charge here. Okay? So the equation is that Cox, this is Cv equals Q, right? Cox times the change in voltage across the capacitor, which is delta Vg minus delta Psi-S. So that's actually the change in voltage across the capacitor. is the same charge as C dep times delta psi s. So that's the basic equality, which says the charge is constant. And now we can take the term psi s and move it to this side, and we see Cox delta Vg is Cox plus C dep times delta psi s. And now we can get exactly what we want, which is delta psi s over delta Vg, which is Cox over Cox plus C dep, and that's defined to be kappa. And now I want to give you some intuition why that is so, or what's the effect of that. What it says is if Cox is really, really big, or this oxide is very, very thin compared to this depletion capacitor, then kappa is going to be close to 1, right? Because Cox will dominate here. And the reason that's true, and that's what we want actually in a transistor, we want the gate to control the surface potential almost perfectly. We don't want it that the gate moves a lot and the surface potential hardly moves. We want them to move together. And that will happen if this capacitance is big here, because this charge here on this capacitor will cause the same charge here, which causes a voltage across here, would cause a much bigger voltage across the other capacitor because the plates are separated by more. And if you cause a bigger voltage across C dep, that means there'll be a smaller voltage across Cox. And so that means delta Vg could better control delta psi s, right? Because the voltage across here won't change much. This voltage will be big, which is what we want. So that's why we want a big Cox compared to C dep in order to well control the surface potential. Okay, so now we can work out the equations for the subthreshold FET completely, because we now know how the gate voltage affects the surface potential, and you can just work it out here. The forward current is IF, the reverse current is I0, and the off current is IR, and the off current is I0. And if we put that in here, we find out that I is equal to I0 e to the kappa Vg over Ut, this is the thermal voltage, times e to the minus Vs over Ut minus e to the minus Vd over Ut. It's equal to the forward minus reverse current. That's the basic subthreshold NFET transistor current equation. And you can break it down and say that the forward component, which is often the only one that really matters, is just this form. It's either the kappa Vg over Ut, either the minus Vs over Ut. Another way to write that, well, and then the reverse component is just the other part. It's just all the same, all different ways of writing the same thing, splitting it up. So now let's look at this surface potential as a function of Vg in reality. I just told you that psi s follows Vg because of the capacitor divider with a slope of kappa, which is the capacitor divider. And that's true as long as the surface is just depleted. Right? But as soon as you go into inversion where the surface potential gets pinned by the charge that comes in from the source, then the surface potential stops changing linearly with Vg. It kind of becomes almost constant. And what do you think happens in this region right here? You're making the gate voltage higher and higher, but this psi s is not changing. What's happening in that part? How is the voltage getting taken up? Well, it's cool. What happens instead of the voltage going up, the charge goes up. You'll see next week. But that leads to this kind of relationship where in subthreshold it's exponential, and above threshold the current hardly changes with voltage because of this pinning effect. Okay, so the log base E slope of this curve is just kappa over Ut, right? This axis is voltage, so it's in the bottom here. And the kappa is determining this log base E slope. So if you take the natural log, the numerical slope would be kappa over Ut or some 1 over voltage. But and the other characterizing thing about a subthreshold transistor is the intercept here. What is the current when the gate source voltage is 0? And it's not 0 amps, right? It's actually some finite current, because even when all the voltages are 0, there's still a built-in barrier, but the concentration at the source end is definitely not 0. There's some femtoamps or maybe even picoamps of current flowing through the transistor. So this intercept here, which in this case looks to be about 10 to the minus 15 amps, 1 femtoamp, is the I0 that goes in front of the equation. And that's temperature dependent. Now, the NFET also has a threshold, and we're going to talk about that a lot more next time. But in this particular case, you can observe that the threshold voltage is around here, and the threshold current is around 5 microamps. So the way you get that is you take the subthreshold current and you extrapolate it up until this subthreshold current is about double on this log scale. It's not much. Is double the actual measured current, and you define that to be the threshold voltage, where this IDS is half of the extrapolated value. In this case, it comes out to be 0.85 volts. And the current at threshold, or the threshold current for this particular transistor, with its W over L, turns out to be about 5 microamps. So as long as you're below 5 microamps here, you're basically operating in subthreshold over these 7 decades of current. And now you can try to measure that stuff yourself in this AMS 180 nanometer technology. What is the threshold current for the different transistors that you're going to measure? It's kind of a good number to know. So there are different regimes of subthreshold operation which are dependent on the drain source voltage, the voltage across the channel of the transistor. The so-called triode or linear region is characterized by this equation where you rewrite it in terms of e to the kappa VGS times some term that only depends on VDS. And you see it's 1 minus e to the minus VD minus VS. So this e to the minus VDS here term quickly goes to 0, of course, when VDS is bigger than 100 millivolts or so. And so when the forward to reverse current ratio is bigger than a few, like 10, you reach so-called saturation, and all the current is just forward current. And in that case, the forward current is just e to the kappa VG minus VS. Notice the kappa is just in front of the VG here, right? Not the VS, because there's no capacitive divider for the source. So it's e to the kappa VG minus VS, and the saturation is defined when VDS is bigger than a few UT. And so now let's look at what that drain source current looks like as a function of drain source voltage. Okay, but before I do that, you can also rewrite, and I often do this when I'm doing calculations, we can write the voltage in units of the thermal voltage, UT. And when you do that, it looks particularly simple, right? The UT just goes away, and you have very simple equations for subthreshold current. Okay, so here's an NFET drain curve of the current versus the drain source voltage for long transistors, where you don't have weird short channel effects. So in this so-called ohmic region, which is for VDS less than about 100 millivolts, or VDS less than 4 kT over Q, you have kind of linear drain source current. Actually, it's only linear for maybe 50 millivolts or so. But then once the voltage gets bigger than 100 millivolts or so, the current just becomes constant. It's just forward current. And then the current here, as a function of different VGSs, just increases exponentially. Each one of these is separated by 100 millivolts. And you can see for 100 millivolt, say from 0.3 to 0.4 volts, the current increases by about a factor of 10. And this whole region out here is called saturation or drain saturation. Okay? This is ohmic or triode. This is the saturation region. And very often you operate such transistors in saturation, particularly in amplifiers. Okay, so now what about this pre-exponential I0? The people that like device physics are not satisfied that we haven't calculated I0. Well, I'm not going to calculate it because it's a complex calculation and there's not much you can do about it. It's just a function of the process technology. But this I0 here comes from the built-in barrier and the doping concentrations. It takes the form I0 is NS UT squared beta of temperature times exponential of e to the minus kappa VT over UT. This NS is a kind of dimensionless source concentration in number per unit volume. This UT times beta is the mu-C-ox W over L that you're going to hear about, mu-C-ox that you're going to hear about next time, but it accounts for the diffusivity of the transistor. And there's another factor of UT that comes from the density of states. And the most important factor in I0 is the e to the minus kappa VT. What's VT? VT is the threshold voltage over UT. So what this says is that I0 is directly dependent on the process threshold voltage. The higher the threshold voltage, the lower I0. The higher the threshold voltage, the harder it is to turn on the transistor, And naturally, the lower I0 is. But I0 is exponential in this threshold voltage. That's the important thing. And that affects the matching characteristics of the transistors. So they become log normal distributions in terms of I0. Now I'm going to tell you about P-type MOSFETs. We talked about N-type, now we're talking about P-type. It's exactly the same like an N-FET, except that now the P-FET lives inside an N-well, which is the back gate. It's usually tied to the positive power supply voltage, and all the voltages are flipped. So this N-well is always the highest voltage in your chip, so that the N is always higher than the P, and so that all the junctions are at least zero bias and mostly reverse biased. But you have the same source, gate, and drain voltages. The gate, drain, and source voltages are always less than this well voltage, which is VDD, and the source voltage is bigger than the drain voltage in this case, not less than it. And so all voltages are referenced to this V-well, which is usually VDD, the positive power supply, and you can draw the voltage connections to the P-FET like this. So if you look at the equations for a subthreshold P-FET, you see that there's a source, gate, and drain voltage. There's a forward and reverse current. And the only thing that's different is that all the voltages are flipped. So instead of having a plus VG minus VS, you have a minus VG and a plus VS and a plus VD. But it's just the same as before. Forward, and it's just a difference between forward and reverse currents, where now the forward current, this one here, is equal to minus e to the minus kappa VG plus VS. So it's like e to the minus VGS, right, that you had for the N-FET. So if you look at the P-FET subthreshold operation, writing V in units of UT, again, it's simple, and it's easy to see that all the signs are just flipped here, right? In the saturation region, which is simplest, the forward current is just equal to I0 e to the minus VG plus VS, or e to the minus VSG. The simplest way to look at these transistors, the N-FET and P-FET, in terms of their functional behavior, is to think about the gate controlling is a kind of a transconductance control on the transistor, right? A conductance is the change in current with voltage, and a transconductance is the change in the current through the transistor caused by the gate, which is a different terminal. And then the source has a very big conductance because the current is exponential with the gate source voltage when the drain source voltage is big, even not when it's saturated. So the source always acts like it has a conductance. But in terms of the drain, as long as the transistor is saturated, this transistor is trying to make basically a constant current that doesn't depend on the drain voltage. So it's acting like a current sink. The P-FET is just flipped around, right? So now you have a source conductance on the top. The gate is still the transconductance. The well is just a reference potential, usually the power supply. And now the transistor acts like a current source that's pushing current out instead of a sink, like for an N-FET. And I'll quickly get this intuition about how these transistors act like transconductance elements and current sources and sinks. And so now here's a puzzle for you. Here's a little circuit where you have VN, you have two transistors. You have VN, VOUT, and VB. So the question is, what is VOUT versus VN for this thing? Why is this circuit called a source follower? And how can you use this circuit to measure kappa? And to answer this question, we're going to go over to the whiteboard, or the blackboard in my case.